Lesson 30 is about using the Pythagorean theorem. Now I know we know what the Pythagorean theorem is. The Pythagorean theorem says that if triangle ABC is a right triangle with legs of length A and B and hypotenuse of length C, then A squared plus B squared equals C squared. Okay, like we've said before, sometimes we just say, oh, the Pythagorean theorem is A squared plus B squared equals C squared. Okay, well, that's just the conclusion of the Pythagorean theorem. We have to have the if part as well. This is only true when A and B are the legs of a right triangle and C is the hypotenuse of a right triangle. So we can't drop off the hypothesis and just state the conclusion. I know that sometimes people are lazy and do that, but the whole Pythagorean theorem is that. Okay. And so, in addition to knowing the Pythagorean theorem, we want today to look at something called Pythagorean triples. Okay, so Pythagorean triples, these are whole numbers. Such that A squared plus B squared equals C squared. Okay, so some classic examples. We probably all know that 3, 4, and 5 are an example of a Pythagorean theorem, or Pythagorean triple. So if we had a leg of length 3 and a leg of length 4, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. The square root of 25 is 5, so the hypotenuse would be 5. Okay, these are all whole numbers. Okay, so these have to be whole numbers for them to be called a Pythagorean triple. Probably another common one that a lot of people know is 5, 12, 13. So 5, 12, 13 is another one where 5 and 12 are the legs of a triangle and then 13 is the hypotenuse. Okay, so 144 and 25 is 169. The square root of 169 is 13. Now there are actually a whole bunch of Pythagorean triples, and it's a good idea to actually be familiar with them because it can help you easily find missing parts of right triangles. Of course, these have to be right triangles. Okay, so I've given you a list of them. These are certainly not all of the Pythagorean triples, but these are Pythagorean triples up to length 100. So now there's, okay, kind of stops here. This is the biggest number before 400. The next one would be in the hundreds. Okay. Now the other thing to note is that if 3, 4, 5 is a Pythagorean triple, then I can always get another Pythagorean triple by taking these numbers and multiplying my Pythagorean triple by some constant. So if 3, 4, 5 is a Pythagorean triple, then if I took 3 and multiplied it by 2, and 4 and multiplied it by 2, and 5 and multiplied it by 2, I would get another Pythagorean triple. I would get 6, 8, 10. Okay, that's a Pythagorean triple, and we could verify it. So if I had 6 and 8, that would have 36 and 64, which is 100. Square root of 100 is 10. Okay, so if and then I could take this and multiply this by double this. So 5. So if I did 10, 24, 26, that would be a Pythagorean triple. Or if I tripled all of these and did 15, 36, 39, that would be a Pythagorean triple. So I can always get a new Pythagorean triple by doing a constant multiple of a Pythagorean triple that I already know. Okay, and the bottom of this sheet shows examples of different Pythagorean triples. So the ones that are marked primitive, okay, are ones that have at least one prime number. Okay, so 3, that's not a multiple of anything. So that's 3, 4, 5. That's called a primitive Pythagorean triple. Notice it's listed up here. All of these ones are primitive Pythagorean triples. So we could even label this primitive Pythagorean triples. Okay. Okay, so this has a 3 in it. And then 5, 12, 13 is a primitive. 6, 8, 10. Okay, and this tells you this is doubling the primitive triple 3, 4, 5. And then 7, 24, 25 is a primitive. 8, 15, 17 is a primitive. 9, 12, 15, we got that by tripling the 3, 4, 5. There's another one that has the number 9 in it. 9, 40, 41. That's a primitive. So notice this is going up in order. So there's only one Pythagorean triple that has an edge of length 10 or a leg of length 10, but there's one with 11. There's a couple different ones that have legs of length 12, a leg of length 13, 14, 15. There's 3 of them with 15s in them. Okay, so 2 of them are, one of them is a multiple of the 3, 4, 5, one of them is a multiple of the 5, 12, 13, and one of them is a primitive. So this gives you all the way up to a leg of length 40. Okay. So some of them are primitive. The primitive, these primitive ones stopped here at the 97. So back here's, where is that one? 65. Oh, that's not even on here. Okay. But so it's helpful to know your Pythagorean triples, because sometimes when you're given a triangle and you're trying to find missing sides, if you can recognize a Pythagorean triple, it's easier to get it that way than to go through the whole a squared, b squared, c squared things, especially for large numbers. Okay. So let's look at some examples. So we need to find the missing side lengths. So when you see something like this, we could start by just going 24 squared plus x squared equals 26 squared. But then when you have to start squaring numbers like 24 and 26, those are probably things that you haven't memorized. Do you know what 26 squared is? Probably not. Okay, but if you see, well, 26 is an even number. This is 2 times 13. That's prime, so I know that it's not going to be, but what is this? This one is 2 times 12. So these are both a common multiple. So is there one that has a 12 and a 13 in it? So I can go over here. Oh, look, there is a 12 and a 13. So if this was 2 times 12 and this was 2 times 13, the missing leg down here has to be 2 times 5. So there's my 5, 12, 13 Pythagorean triple, and if I do all multiples of 2. Okay, so I can easily get that x equals 10 inches, and I don't have to go through even trying to figure out what 26 squared and what 24 squared is. I can just do this a little bit of easy factoring and match that to a Pythagorean theorem that I know. Much easier. Okay. Let's see about this one. So this is 2 times 3. Okay. So, I could write this one as 2 times 6 or as 3 times 4 because I don't know which one is which. Okay, actually there aren't any Pythagorean triples at all that have a leg of length 2. So, okay, it couldn't be 3 times a multiple of 2. We can throw that one out. Okay, do we have a Pythagorean triple that has a 3 and a 6 in it? No, this one has a 3 in it. That's the only one with a 3 in it. So it's not a Pythagorean triple, but at least we checked to see if we could get out of it the easy way. And, all right, that's not going to work, so I'm going to have to go to the 6 squared plus 12 squared equals x squared. Okay, 6 squared is 36, 12 squared is 144, and when I add 36 and 144, I get 180. And so that means x is the square root of 180. Now we want to write that in simplified radical form, so we should factor that. Okay, so let's see. That would be 9 times 20, and 20 is 4 times 5. Okay, so we know that the square root of 9 is 3, so we can bring a 3 out. We know the square root of 4 is 2, we can bring the 2 out. We don't know the square root of the 5, we got to leave that in there, so this is 6 square root of 5. Okay. Then, again, so we've got a 5x10. So the only Pythagorean triple with a 5 in it is 5, 12, 13. That doesn't match. So this one is not going to be a Pythagorean triple. So we got to go ahead and go through the Pythagorean theorem formula. So we've got to do 5 squared plus x squared equals 10 squared. So this is 25 and this is 100. That means x squared is 75 and x is the square root of 75. Okay, 75 is 25 times 3. We know the square root of 25 is 5, so we can bring a 5 out and we're left with 5 square root of 3. Okay. So it's always a good idea to check your Pythagorean triples to see if that helps you. If not, then you can just write your go through the Pythagorean theorem formula and make sure to write your answer in simplified radical form. Okay, let's do some of the lesson practice problems. So we want to find the hypotenuse. All right, so 21 is 3 times 7. Okay, this isn't divisible by 3 or 7. Okay, so it's not a multiple of 1, but let's look and see if there's anything with a 20 and a 21 in it. Well, sure enough, 20, 21, 29 right there. And so the hypotenuse is 29 yards, and I didn't even have to do any work if I know my Pythagorean triples. Okay, so 23, 20, 21, 29, and this is a Pythagorean triple. Okay, how about find the missing leg? 40 something 41. Okay, let's look in here. So, here's a 40 and a 41. 9, 40, 41. So, x is 9. 9, 40, 41, those are all whole numbers. This one is also a Pythagorean triple. Okay, now we need the hypotenuse. Okay, so 6 and 14. Okay, so 6 and 14, those don't appear to be in here. What about, those are both, if we did 2 times 3 and 2 times 7. So what about 3 and 7? Well, the only one with 3 is 3, 4, 5. This one isn't a Pythagorean triple, so we've got to go ahead and use the formula. So 6 squared plus 14 squared equals c squared. Let's see, 6 squared is 36. 14 squared is 196. Okay, so when we add those, that's 12, 13, 232. Okay, and let's see, so that means c is the square root of 232. All right, let's see if we factor that. Let's see, 232 divided by 2, it's 2 times 116. 116 is divisible by 4. So 2 times 4 times 29 is what we have in there. Okay, and let's see, we only know the square root of 2. 29 is prime. So we can bring, sorry, the square root of 4. So the square root of 4 is 2. We can bring a 2 out, and we have to leave 2 times 29 in there, which is 58. So that will be C. Okay. And our last problem. All right, a ratio of a TV's width to its height. Okay, so imagine we have a TV. And the ratio of its width to its height is 16 to 9. Okay, so if this The ratio would be 16 to 9, oops, not 19, 9. So you can think of this as 16x to 9x. Okay, so I don't know what x is, but they're always going to be in that ratio. Okay, so the width is 32. Okay, so the width is 32. So if this is 32, well, this is 16x to 9x. That means that this one has got to be 18, right? This x is 2. So this is 18. And we want to know what the length of the diagonal is. Okay, so what's this? I'll call this D for diagonal. Okay, so we could go through and do the whole Pythagorean theorem, but probably before we do that, it might be good to see if we have a Pythagorean triple hidden in here. Okay, and so this one is divisible by, we could write this as 2 times 9, but this, and then this is 2 times 16. Okay, or we could write it as, well, this is only divisible by 2, so this is not divisible by 4 or anything else. So we could check, is 9 and 16, are those values that are in here? So no, there's a 9, 40, 41, okay, but not a 9 and a 16. So we're not going to be able to find a Pythagorean triple. We'll have to go ahead and just figure out the length of its diagonal. Okay, so we have to use our 18 squared, which is the one leg, plus 32 squared is the other leg, equals D squared. Okay, so this one we'll probably need to break out the calculator. 18 squared is 324. 32 squared is 1024. Okay, so 1024 plus 324 is 1348. So that means D is the square root of 1348. All right, well, that's definitely divisible by 4, so let's start there. So 337 times 4. Okay, what is 337 divisible by? Not 2, not 3, not 4, not 5, not 6. And not. Are there any strange primes? No, 13. Okay, I'm just going to call it good at 2 times the square root of 337. Okay. All right, so, and that would be in inches. All right. So, hopefully that's mostly a review, but you might want to go ahead and memorize a few Pythagorean triples, especially like these first 1, 2, 3, 4, 5 that come up a lot. I mean, those are probably the most common ones that you're going to see in problems, and memorizing those will often save you some time in solving problems if you already know, because notice that those lead to a whole bunch of other ones as well.